Okay, welcome to lecture here. We're going to continue on chapter 3, then we're going to roll into chapter 10. Again, make sure you put here in the chat. Okay, so we've been on chapter 3 here, and chapter 3 started talking about matter. We kind of finished up a little bit last time talking about mixtures and pure substances. A reminder that a pure substance is anything that's pretty much by itself, not really mixed with anything. So as we were talking about at the end there last time, if you have just water by itself, that's a pure substance. If you have just salt by itself, that also is a pure substance. It's when you mix two or more sort of pure substances together that you do get mixtures. And mixture basically is the combination of two or more substances where they both retain their identity. So even though, again, it may look like, something disappeared, something's gone, something changed, the pure substances are still there in their original form. As we'll talk about here to finish up this chapter, you can get back those original substances by some type of physical means. So you could use some type of physical process and you'll be able to get back those pure substances in their original form. So let's talk about actually mixtures. And there's really kind of two types of mixtures that I think we touched upon last time at the end, but here let's just officially kind of talk about it. The first type is a homogeneous mixture. And really in a homogeneous mixture is thought of as being the same throughout. So basically after sufficient mixing, when you mix it together and you look at a homogeneous mixture, it does have the appearance of just being basically one thing. So it look exactly the same throughout. So I think salt water we were talking about at the end there. Again, if we took just water by itself, a pure substance. If we take salt by itself, a pure substance. And when we put both of these together to make something like salt water, this is a homogeneous mixture. Again, if you look at salt water, or if you have salt water, you take just the water out of, say, the ocean, nothing else floating around in there. Again, it just appears to be water. It looks the same throughout. But again, if you tasted it or something like that, you'd be able to taste the salt that's in there. You won't be able to kind of see the salt that's in there. And again, that's basically a homogeneous mixture. So usually with sufficient mixing, everything sort of becomes one layer, sometimes called. And you don't see these sort of different layers that occur in other types of mixtures, which we're talking about next. So again, there's an example of the salt and the water. You put the salt in the water, you can mix it. It definitely will dissolve. But again, if you look at it, it just really has the appearance of just water, just one sort of layer, no difference in there. And again, even though, as we'll talk about here in just a second, even though it appears that all the salt has maybe gone away, it's changed, it's totally gone, it actually is still there in its original sort of form. And here's some other examples. Air, as I think we touched upon at the very end as well last time. Air really is a mixture. It has nitrogen, oxygen, argon, other gases, carbon dioxide, depending on sort of where you're at. But again, when we look at air, for example, it all looks the same throughout. Hopefully you don't see things floating around in the air in most cases. Brass as well. Brass, again, a kind of a mixture of a couple of metals together, but it looks sort of the same, like one sort of metal, even though there's other pieces or types of metals involved in brass. Now, that's different than a heterogeneous mixture. And in a heterogeneous mixture, unlike a homogeneous mixture, you pretty much will see the different layers. So you can mix the thing all day. You'll never get them to basically look the same throughout. So like the lab today, and I think an example we'll see here as well, if you take water, which is again a pure substance, if you take sand and you basically put those together, you're going to get sand plus some water. And you can mix that sand all day. It will never dissolve. It'll never go away. You will still see the sand in the water as sort of different layers, if you will, and or different phases, is sometimes called. And that's your heterogeneous mixture. Again, you will always sort of see different layers. Chocolate chip cookie, right? If you cook a chocolate chip cookie, you see the chocolate chips in it. Even if you mix them and cook them, yeah, you see different sort of layers in it. Oil and vinegar salad dressing as well. That's another common sort of example. If you've taken oil and vinegar salad dressing, you mix it, right? It does sort of mix for a bit, but if you leave that oil and vinegar salad dressing, what eventually happen is, right, they will kind of layer out, which is why you always got to kind of mix it. And that's, again, a heterogeneous mixture. So homogeneous, everything looks the same throughout. Everything mixes. If it's like a solid in a liquid, the solid will dissolve in the liquid. It will all look the same. Heterogeneous, we see different layers that are there when they mix together. Any questions on that? Now, regardless of whether it is a homogeneous mixture or a heterogeneous mixture, the important part about a mixture is, as I mentioned before, that everybody basically retains their identity. So they are still really there. They're still really there, and they're really their same form. This is all really physical type of changes that are occurring. There's no chemical changes that are occurring when you make a mixture, because nothing's really changing into anything new. Again, it may just have an appearance that it's gone, may look a little different, but ultimately what you start with and what you end up with are still the same fundamental things. So for example, the salt and water, we'll talk about in just a second. You can separate those two guys out and get back the salt and the water just like it was originally. The sand in the water as well, you can definitely separate them out by some type of physical means. So when we look at this, which of the following is a homogeneous mixture? So again, remember, homogeneous is the same throughout. Pure water would not be a homogeneous mixture, although pure water will look the same throughout. There's nothing else there but water, so it would not be classified as a mixture in that case. That would be a pure substance. Gasoline is a homogeneous mixture. It's a lot of different sort of chemicals together. It looks the same. A jar of jelly beans is the same thing all the way through. Again, kind of like pure water, so that would not be a mixture. Soil is a mixture of different things, but typically when you look at soil, you'd see different layers like rocks and everything's kind of mixed in there, and it's not a homogeneous mixture. And copper metal is a pure substance by itself. So in this particular case, it looks like gasoline, which is a mixture of octane and some other additives added to gas, is typically your only homogeneous mixture, which would look the same throughout. Again, A is not a mixture, C is not a mixture, and E is not a mixture, and soil would probably be more of a heterogeneous type mixture. Any questions on that particular one? Okay. So a mixture has a blank composition, whereas a compound always has a blank composition. So take a second, think about which combination there would work. So in terms of this particular one, a mixture would mixture has a pure composition. That would not be right. A complex, maybe. Constant, variable. It would actually be here, the last one. It has a variable composition, right? Because a mixture could be sand, water, salt. You could put a whole bunch of stuff in there. A compound always has the same composition, so it's a constant one. Again, if you had something like water, which is a compound, no matter what you do, it's always a couple of hydrogens with oxygen, while you could have a mixture that could be sand and water. It could have a mixture of sand, water, metal, whatever else you want to throw in there. So it does have a more variable sort of composition. The brass is a candlestick is classified. So as we saw there, brass is a homogeneous mixture. Again, although it is a mixture of several different metals together, which is essentially what makes up brass, when we look at it, it just kind of looks like, you know, a piece of metal. So it looks sort of the same throughout. So it would be a homogeneous mixture, not a pure substance, because again, it's a couple metals together. It's also not an element also because it's a couple of different metals together. And again, it's not a heterogeneous mixture because again, it looks just like a piece of metal, which looks the same throughout. Now, as I was talking about, regardless of sort of the type of mixture, whether it's a homogeneous or heterogeneous, you definitely can separate out any mixture through physical means. And two common ways that we're going to kind of talk about here is filtration and distillation. And these are two common sort of ways that you could separate out mixtures. And basically the way we do this is we sort of take advantage of a lot of the physical aspects or properties of matter and to help us separate them out. So distillation, as we'll see in just a second, really involves sort of heating a solution up. When we heat a solution up, we can heat it up to its boiling point. At that point, it's going to go from liquid to gas. And that's a really good way, for example, as we will see if we have our salt water, right? So if we have our salt water in here, and we heat it up. When we heat this up, right, all the water part will basically evaporate off. And if you wanted to, which is really what distillation is, and we'll see a much better picture than I could draw, but you could basically have a closed system where you could collect all that steam that comes off and you could make it come back to liquid water. And if you continuously evaporate off the water, you'll be left with really just your salt in that case. States of matter filtration is a really good way to separate out a solid from a liquid. So that's a very good process to separate a solid from a liquid. So that would be really good, as we've been talking about, like our sand and water, right? They put a piece of filter paper in, pour the sand and water, the liquid part will go through the funnel. The solid sand will get trapped on the filter paper, and obviously you'll be able to separate out those out. Chromatography is another way, and there's all kinds of different types of chromatography. We don't get into too much in this class, or really any class, until you take maybe something like biochemistry or something like that. But basically there's different types of chromatography. And one way is, for example, you could have a sort of tube, and inside the tube, for example, you could fill it with something that has, you know, almost like something that's ready to grab something on it. So as you pour your liquid through, you know, as your liquid comes through, some of the particles in there will be attracted to what's in the column, and it will grab out stuff from the liquid, allow the other ones to flow through. And again, there's all kinds of different types of chromatography, but that's sort of the basic principle of that. You know, it's sort of attracted to what you set up. So in a chromatography, you typically set up sort of a system for things to go through, and it'll be able to attract things out of that liquid as it goes through. Volatility, so something's really volatile, it means it goes into the gas phase really easily. So evaporation is a very good way to sort of separate out things. So here's a much prettier picture than I would have attempted to draw there of a distillation apparatus. And essentially, here what we got going on is we have our salt water in here. And this entire thing is really a closed system. And we have this tube over here, which is kept really cold. So as we start to heat up our salt water in here, and again, remember, salt water is a homogeneous mixture, which if you looked at it, you may think, hey, I don't think there's any solid in there at all. It just looks like water. As you start to heat this, as I mentioned before, the steam will start to produce. And again, steam is just water. And because this is a closed system, it essentially has nowhere to go. So it's sort of forced down this tube. And as it comes through this tube, which is really, really cold, if you have steam, which is a gas, and it runs through that cold system, it's going to go through condensation. And it's going to form liquid water at the back end. And what you'll have over here is that liquid water will start to drop into the sort of the collection flask on the other side. And if you continue this process, essentially what you will be left with over here, which might be a little bit harder to see, is sort of like a white residue in the case of you have something like sodium chloride in there. and that white residue would be the salt that was originally dissolved in the water. And obviously over here, you've now separated out the pure water. So this type of mixture, which is basically a saltwater mixture, which is a homogeneous mixture, we were able to, through this distillation apparatus, you can collect your salt back in the original sort of form. Again, you could take this salt at this point and let it sort of dry out, and it would be just like it originally started. You obviously now have your liquid water on this side, and again, also in its original form. So again, even here in a homogeneous mixture where you don't see any evidence of two things mixed together by a process known as distillation, here you're able to get back both of those original substances in their original form. And this again is all a physical type process that's occurring here. And again, as it shows here, it is just a physical change. And that's why mixtures are really physical changes that occur. Again, even though in this little beaker over here, when we look at the salt water, as mentioned, has no clue that there is salt in there. Again, the salt, as you can see on the right-hand side, is in its original form, and you could get it back out. Now, filtration, as I mentioned, is a really good way to use to separate out a solid from a liquid. And typical filtration setup is like this. We have a funnel, and we have a piece of filter paper that's folded inside the funnel, inside here. And as we pour our sand and water mixture in here, the liquid part is going to be small enough really to pass through the filter paper and pass through the funnel and drip down into the bottom. Obviously up here, the paper will catch the sand because it's too big to go through the filter paper. Believe it or not, on filter paper, there's little sort of holes, if you will. You want to kind of think about it, even though you visually can't really see them. But it's only small enough to allow certain size stuff to really go through. Larger stuff really gets caught really on it. And here, through this very simple process of filtration, we have now got back our sand, which is on the filter paper. We could lay out the filter paper, put it in an oven, whatever it is, and just let it dry out. And again, you would have the sand in its original form. And obviously you would have your liquid water as well in its original form in the beaker. So these are two very, very common ways that we could separate out mixtures. And as you can see in each of those examples, the sand and saltwater mixture, the sand and water mixture was a heterogeneous mixture, which we could separate out. And also our homogeneous mixture, we could also separate as well. So to separate out a sand saltwater mixture into a pure substance, one would have to employ, so again, this is actually very much like the lab we're doing today. A sand saltwater mixture. This mixture right here between sand and saltwater is a heterogeneous mixture. And in this particular case, we would want to start with filtration. Again, that filtration using a funnel. When we dump it in here, we're going to get our sand to stay up here in our filter paper. What will actually drip through here in our beaker, way to the right there, will actually be our salt water at this point. And now once we've done that separation, we're actually still left with another mixture, which is the salt water. And the salt water here is actually a homogeneous mixture. And again, that homogeneous mixture of salt water, as we've been talking about, will look the same throughout. And we would want to follow that up through distillation to get to our salt by itself, just like we saw in the last picture, and our water by itself. So we would need to do two steps, because really we have both mixtures here. The overall mixture is a heterogeneous, which we could use filtration to separate that out because we have a solid from liquid, followed by leaving us with salt water, which is a homogeneous mixture. And we could use distillation, heat it up, it will evaporate off the water. You could collect the water, and obviously you'll be left with sand. Any questions on any of that there? Okay. So in terms of matter, matter, again, as we've talked about, can be either a homogeneous mixture. It can be a heterogeneous mixture, which again is a combination of two or more pure substances. Also could be a pure substance, which could be either an element or a compound. And as we talked about in this chapter, remember everything sort of all goes back. The farthest you could get back there is elements. Again, a compound can be broken up into an element by a chemical change. But again, that's as far back as you can go. So in this case, pure substances consist of, as we just saw there, it could be either elements or compounds. And again, that's down here on the bottom. So a pure substance can either be an element or a compound. Elements and mixtures. Mixtures are not pure substances, right? They are actually a combination of two or more pure substances. Elements and solutions. Solutions really are sort of mixtures. Solutions, just so you know, solutions are really homogeneous mixtures. And elements and energy would not be the case. So it looks like the correct answer here would be A in this particular case. And that is the end of chapter 3. Any questions on chapter 3 here? Okay, we're going to roll. Actually, we're going to skip ahead now. We're going to go to chapter 10. So we're going to do some of the higher chapters, and then we'll come back to the lower chapters. So up next is chapter 10, which again should be on the Canvas site. Just give me a second to get it up here. Let me do that. And try that. There we go. Okay, so as you can see, we're jumping to chapter 10, which is about energy. So we'll talk a little bit about energy in this chapter, I think. And like I said, we sort of jumped to chapter 10 and kind of hang chapter 10, I think, and then 11, 12, then we kind of drop back down some of those lower chapters. So obviously we're going to talk about all kinds of different energy in this chapter. So let's just talk a little bit about energy and sort of what it's about. So energy really is the ability to do work and produce heat. There is the conservation of energy. So when we talk about energy, energy is never created, nor is it destroyed. It is converted from one form to the next. So as we'll talk about here in just a second, one type of energy, for example, is something like potential energy. And you can convert potential energy into, say, kinetic energy. So you definitely can transition energy from one form to the next, but we don't lose it. And that's really sort of the idea behind energy. And really, energy is sometimes what is referred to as sort of being a thermodynamic type property. And the idea is, as we will see as well, you know, usually when we talk about this type of stuff, there's something that's known as the system, and there's basically something that's known as the surroundings. And basically, the idea here is something loses a certain amount of energy, somebody else will gain a certain amount of energy. So there's sort of that thought of sort of equal transfer in terms of energy. So for example, if you did a reaction in a test tube and it gave off 5 joules of energy to the surroundings then would pick up that 5 joules of energy. And as we'll talk about in this chapter, one way that we sort of can follow, you know, that energy, is it being absorbed, is it being given off, is in terms of values, whether or not something is sort of negative in terms of energy or positive in terms of energy. And we'll talk about that as we go through it. So the energy content of the universe is constant for that reason, that, you know, you have sort of this thought of as perfect exchange of energy. You know, it just doesn't disappear along the way. Somebody's got to pick it up if somebody loses energy, and vice versa. So let's talk about some different types of energy. Potential energy is the energy that's due to the position of the object. So that's that classic example of, you know, the big boulder on top of the hill, right? that's just teetering on the top there, ready to drop down and crush whatever's underneath it. And it has a certain amount of energy due to its actual position, its physical position. And kinetic energy, which is basically the energy of motion, depends on the mass of the object and its velocity. And this is what we're talking about when something can transform. So we can have this boulder that all of a sudden does tip over the edge there. And as it is traveling down, it's picking up basically a lot of that potential energy is being converted into kinetic energy, which again is that energy of motion. But eventually it will hit the ground, as we will see in a couple pictures in just a second. And at that point, it will come to rest at a new potential energy. But as it hits the ground, it's going to transfer all that energy to the ground, and hopefully nobody underneath it, but would pick up all that energy as it basically comes down. And that's sort of, I think, what we were seeing here in these sort of pictures. Again, A here has a certain amount of potential energy where it's at, so does B. As it travels down, A gets some kinetic energy. It's going to actually hit B and transfer some of that energy to B, which is going to give B some kinetic energy and motion. And again, they're both going to come basically to rest, and they're perhaps a different energy level from which they started. But again, B having this natural potential energy, A is natural, and as it moves, kinetic energy. And again, when they do collide, there's going to be that transfer of energy from one to the next, which is going to obviously, as you can see here in this picture, help promote B up a little bit and come to rest at a different energy level. Now, energy, heat, and work, let's talk about some important sort of aspects of it. Heat is really the transfer of energy between two objects that are basically at different temperature. And as we'll see and as we'll talk about, heat always transfers from higher energy, higher temperature, to lower temperature. So that is usually sort of the flow of heat, how it works. So if something is higher in temperature, it will cool down because it's losing energy, while something lower in temperature will gain that energy. And the reflection of that energy sort of change is the temperature will start to go up. Now, work is some type of force acting over a distance, and we can use energy to either do work on something. It also, something could do work on an object, but work is sort of a way that we can use energy to do something. Now, an important concept sort of in chemistry is the idea of what is known as a state function. And a state function is really a property that does not depend on the system's past or future. So that's a lot of weird words there, but basically it doesn't depend on sort of how you got somewhere. Really, when we talk about things that are sort of state functions, there's really only two parts that's really important: where you started and where you ended. And usually in chemistry, when we do calculations, that's usually when we do things like final minus initial. And that's sort of our idea here. Our final state minus the initial state. It doesn't really matter how you got there. The important part is really ultimately where you started and the overall ending of where you ended up. So for example, we may see a picture of it, but if we had like a mountain or something like that, and we had two people, an A and a B person, and the A person just hiked straight up the mountain to the very top. The B guy decided to take, sort of the scenic route around the mountain, and ended up pretty much in the same identical spot. Now, in terms of A and B at this point, in terms of their potential energy, they both have really the same potential energy. It didn't matter that A took the more direct route to get there, B took the more scenic route to get there. The ultimate part is they both kind of started at the bottom, both ended up at the top, and they both now possess basically the same state function. And really, a couple of things where state functions sort of come into play is in terms of energy. Energy is a state function. It doesn't matter, if it happens in one reaction, two reactions, three reactions. So when we look at a reaction, for example, reactants that go to products, And this is typically what a chemical equation or reaction it looks like. The reactants are our starting materials, and the products are ending guys, basically. So ending. And when we talk about chemical reaction, this is usually what we're talking about, sort of final minus initial. This is really our final state, our products, what's being produced. Our initial state is really our reactants, what we started with. And really the difference between sort of your product minus your reactants, for example, in terms of energy, is a way that we can figure out what's happening in terms of energy in a reaction. But not all reactions do really occur as they may seem in an equation. Sometimes you see a chemical equation, it's like this goes to this, and you sometimes think that it just happens in one step. It just completely goes from one step to the next. It may not. There's a lot of reactions, for example, that, you know, you may go A plus B goes to C plus D, then like C plus D goes to E plus F, and the overall reaction is A plus B goes to E plus F. And really, these guys are formed along the way, but we never see them in the overall reaction. But it does happen in sort of a stepwise fashion. So a lot of chemical reactions actually do take place in multiple step type things. So when we talk about energy for reactions and stuff like that, state function is an important part of that, because it doesn't matter if this reaction occurred in 1 step, 5 steps, 6 steps. The overall change in energy that occurs is what we end up with on our product side from where we started with on our reactant side. So changes in state functions are really independent of pathway. Again, as I mentioned, energy is a state function. Work and heat are not state functions, but energy is a state function. Heat and that work is not. So state functions, distance traveled from one location to another is not a state function. The distance, right, it does depend on the route taken in that case, right? So, you know, if we just drove straight, or we did a side tour to go see a couple of, you know, tourist stops along the way, if you're driving somewhere, you would end up with a lot more miles, right? If you kind of detoured off the highway and hit all the little stops along the way, all the little lookout points and stuff like that, right? As opposed to if you just ignored all that and just drove straight through to your destination. In terms of your distance traveled, like your miles traveled, there would be a difference. Change in elevation is a state function, so sort of the same idea. Again, if you were driving up a mountain, right, and you got to the top of the mountain, and again, if you just went straight around the mountain, you know, and got to the very top, you would be at the same elevation as somebody else who went up the mountain, got off at each individual little town along the way, and kind of visited, came back on the main road, and ended up at the very top of the mountain as well. Again, that sort of position of where you're at that moment is sort of a state function. So in terms of some stuff we talked about here, energy associated with the position of an object is the potential energy. Again, that's like the big boulder on top. It has a certain amount of potential energy would be its position. The property of a system that changes independent of its pathway is, again, as we've been talking about, our state function. So again, state functions independent of pathway can happen in multiple steps. It's just important where you start and where you end up with. So talking about temperature, temperature really is a measure of the random motion of components of a substance. Now, temperature and energy are really different in terms of that. So a lot of times when we talk about energy and sort of relationship to temperature, temperature and something that's referred to as thermal energy are different. Thermal energy is basically the energy associated with the amount of molecules or atoms present. So the more molecules, the more atoms, the more thermal energy you would have, not necessarily more temperature. So there is a distinction between that. And we'll take a look at this example here in a second. But for example, say you had a cup of coffee or something like that. at say 90 degrees Celsius, whatever it is, or water, and you had like a big bathtub, say 40 degrees Celsius, right? Now, in terms of thermal energy, not temperature, but in terms of thermal energy, the actual bathtub, even though it has a lower temperature, would actually have a higher thermal energy, because in a bathtub, there is a lot more particles or molecules of water floating around. More water molecules, more motion of those molecules, more thermal energy. Although the cup of, say, water or whatever it is on the left-hand side there has a higher temperature, it has a lower thermal energy because there's less molecules moving around in there in terms of their energy. Guy on the left has a higher temperature because even though there's less molecules, is in a very smaller sort of area, right? So those guys and those motion of those guys is going to result in a higher temperature than in the bathtub, where there's a lot more room for those guys to move around. So sometimes people oftentimes get confused in the idea that temperature and thermal energy is the same, but really temperature is a measure of the motion or random motion of what's in that substance. So however they're flying around. So obviously in a smaller area, they're going to be, even though there's less molecules, they're going to be moving around a lot more, as in here where they have a little bit more room to kind of spread out. And that's why we see a lower temperature here versus what I just scribbled out on the left there, the higher temperature on the left. But in terms of the actual thermal energy, the guy on the right would have more because there's more molecules in there. So there's a slight distinction between them, and it's really not the same thing, those two things, but it's very oftentimes sort of confused and sort of thought of as being the same. So here we have two guys that are at different temperatures. We have 90 degrees water on the left and 10 on the right, and this is sort of an insulated container. So heat again is going to flow from hot to cold. So our 90-degree guy is going to start to cool down, and our 10-degree guy will start to heat up. And eventually, in that particular example, as we saw there on this last slide, honestly, they'll probably meet somewhere in the middle there, maybe 50th degrees. They'll eventually come maybe to equilibrium somewhere, you know, halfway between the adding those two temperatures and dividing by two, excuse me. So as I mentioned before, heat is really the flow of energy between two objects that are at different temperatures. And again, it always goes from that hot object to the colder one. So in that last example, like I said, the 90-degree guy will start to cool down as it loses energy. As it loses energy, they're no longer moving around as fast. And that basically temperature, which is a measure of that motion, is going to start to come down as well because they're not moving as fast. The guys that were lower in energy is going to pick up some of that energy, and they're going to start moving around a lot faster. And you're going to see a reflection of that as the temperature starts to increase as that occurs. So some common units of energy are calories and joules, and there's a couple different types of calories. Calories written like this with the capital C, or sometimes referred to as nutritional calories. While we do have calories, and I'll just write it like this, our CAL, lowercase c, is also more in terms of what in chemistry we use is the calories with the lowercase c. You may say they kind of look the same. What's the difference? So the difference is 1 calorie with a capital C is equal to 1,000 of the little calories, the little c, and that is also sometimes referred to as another common unit, 1 kilocalorie, which is 1,000 of the little calories. So again, the capital C with calories, more nutritional calories, they're equal to 1,000 of the little guys, the little c's, and again, that's 1 kilocalorie, which is a common unit. Joules is also a very common unit, and kilojoules is also another common unit. And again, in 1 kilojoule, there's 1,000 joules. So that's a common conversion between them. Also, there's 4.184 joules in 1 calorie with a lowercase c. That's also another very common conversion that's used a lot in energy, is that relationship there. Any questions on that? So as you can see here, as we've been talking about, heat does not really equal temperature. Again, temperature is sort of a manifestation of how fast everything is moving. But again, heat and really energy has a lot to do with the amount of molecules or particles that are present, while temperature is sort of a measure of how fast those particles are moving and sort of relationship of that. As you can see here, both of these campfires obviously would give off heat, but they both would obviously have a different temperature depending on, obviously the guy on the right probably would have a higher temperature maybe than the guy on the left. So as we can see here over time, what we see is what we've been talking about. Again, that guy on the left there would go from 90 degrees, giving up a lot of that heat and energy. The guys over here on the right-hand side would pick up some of that heat and energy. They will start moving around a lot faster, which is why we do see sort of an increase in their temperature. As these guys over here on the left lose the energy, they sort of move around a little bit slower. The relationship of that is we start to see a decrease in their temperature. And again, as you can see here over time, if this is all insulated sort of container, we would expect them probably to level out about halfway through that, right? 90 plus 10 is 100, 100 divided by 2 is 50. So we'll probably end up halfway there in terms of temperature between those two on each side. Again, nothing is lost in terms of energy. So this is sort of that idea of the law of conservation of mass. The hot water on the left is losing a bunch of energy. The cold water on the right is gaining the energy. So again, no loss of energy here being transferred from kind of the left-hand side to the right-hand side in this particular case. And that does bring us to the idea of system surroundings, as I mentioned earlier. The system is really the part of the universe that you're interested in. So a lot of times in chemistry, if we did an experiment or a reaction in a test tube, maybe we did it in a beaker, whatever it may be, that's a lot of times the system that we're dealing with is sort of the chemical reaction that's taking place in chemistry. And again, like I said, in the lab, it's whatever you may be mixing that in. Beaker, flask, graduated cylinder, whatever you may be doing it in. And the surroundings is really everything outside of that, so those are really the two things. And like I mentioned earlier, this is sort of what we sort of think about in that conservation of energy. Like I said, it's sort of a back and forth in that sense of if the system lost a certain amount of energy, the surroundings would gain, and vice versa. Surroundings lost a certain amount of energy, the system would gain it, and we would not lose anything along the way. And again, as we will see here shortly, the number or numerical value, if you will, for the energy that's either being lost or gained is going to be the same for the system or the surroundings. So again, if the system lost, say 5 joules of energy to the surroundings, for the system, it would be negative 5 joules because that means the energy is being given off. For the surroundings, it would gain 5 joules of energy, positive 5 joules. And again, that positive, negative, as we will be talking about here in this chapter, is a really important aspect of numbers and numerical values that you get to help you really understand in terms of energy what's happening. Is it giving off energy or is it gaining energy? And that's really what these two words basically mean here, exothermic and endothermic. Exothermic, as we will see, is when heat and energy is given off, is released. And as we will see in terms of energy values, that is usually accompanied by a negative value in terms of the number, while endothermic, as we will see, is when heat and energy is absorbed. And that is usually represented by a positive value. So in my example here, I was talking about the system and the surroundings. The system is losing that energy or giving off that energy. So that's why we say for the system, in my example there, it would be negative 5 joules of energy, while the surroundings would be the thing that would pick up all that energy and absorb all that energy. And that's why it would be positive 5 joules of energy. The actual numerical value, as you can see in this very simple example, is 5 and 5. So the actual value of the energy is the same. And again, that's the idea of that conservation of energy. We don't lose it nor create it, is just transferred from one place to the next. So this is what is sometimes referred to as an energy diagram, and sometimes you will sort of see it drawn like this. It's like a little hill, if you will. And here we have energy on the Y, we have sort of the reaction happening on the X. And in terms of energy, the important aspect of this is an endothermic process. So what we see here is our reactants, which is our starting material in a chemical reaction. Is lower in energy than our products, which is obviously the stuff that has been formed as a result of a chemical reaction. And as I mentioned before, when you've seen a chemical equation, which they assume since it's chapter 10, you've seen it, which we haven't technically seen it yet, but that's why they talk about all this stuff, obviously. Reactants, again, on the left-hand side of the arrow is what we start with. Products on the right-hand side of the arrow is what is formed as a result of our chemical reaction. And whenever you see this sort of energy diagram here, this is when the reactants are lower in energy than the products. You could just think about it. In order for those reactants to get up there in terms of energy, it needs to absorb energy, right? It needs energy needs to be kind of be put in there for those reactants to get up there in terms of energy. And again, this is your classic endothermic sort of diagram that occurs. Now, you oftentimes will see this sort of hill that it climbs, and we'll just mention, since we sort of have it here, what that hill is. That hill from where the reactants are to the very top of the hill is also another type of energy, which is sometimes referred to as the activation energy. And that's sometimes abbreviated with E of A. And the activation energy, as you can kind of see, is the hill that the reactants has to climb basically to get to the other side, to get to your products. And the activation energy is the minimum amount of energy required for a reaction to take place. And some other things that you'll see activation energy, if you continue on to 1B, for example, it obviously determines how fast a reaction occurs, right? Big hill here. I get all the way up and over this hill to get to the other side. It's going to affect how fast or slow a reaction is really that hill. And what happens in a reaction is basically the only thing that happens is these guys start to break apart in terms of their bonds, and they form new bonds on the other side. And that's all occurring as it's climbing this hill. So it needs a certain amount of energy to start breaking those bonds, making new bonds. And really, when it gets to the very, very top, that is sometimes referred to as the transition state. I went blue on blue there, but that says transition state up on top. So transition state is the very top of that hill. And again, as you'll talk in more and more detail if you go to 1B, but basically at the top of the hill in the transition state is a sort of guide that is something that has partially broken bonds, partially made bonds. It's really this thing where it's sort of transitioning from the reactants into the products and the stuff that's being formed. One important part about energy and stability, as we'll learn in chemistry, is the higher the energy, not so stable. Things really do not like to be in high energy. Much like us, we like to be in a lower state of energy, and same thing in chemistry. So things that are typically highest in energy are not very stable. They always want to kind of get themselves back down to as low in terms of energy as they can. And that's sort of the most stable sort of aspect of it. And as you can see here, this is the worst part in terms of energy, the transition state. It's the highest in energy. And that's why there's a thing that's known up on top there, which is the transition state complex. And that's something that's very hard to isolate, because usually once it gets up here, because it's so high in energy, you have these things with partially broken bonds, partially made bonds, that it very quickly kind of drops down to the other side to get to the product. So it doesn't hang around a very long time, because as you can see in this diagram, it is sort of your peak of energy in terms of the height of energy. And that's different than sort of an exothermic process here, where we sort of see the opposite. And in an exothermic process, for example, I'll kind of complete the curve here, coming down. Something looks like this. We have our reactants, which are actually higher in energy than our products. And whenever you see a diagram where the reactants, which is your starting material, are higher in energy than your products, it is always an exothermic process. So in order for this reactant to get down in terms of energy to our products, it needs to give off energy. And that is a exothermic type diagram. So exothermic, as we talked about, is when heat and energy is released or given off. And we also can see here in this diagram, much like the other one, there is also really a activation energy or hill that it has to climb. And that would be right about there. That's the activation energy. And just by this really bad drawing I did here, you could take a look at this hill here. And if you take a look at the hill on our endothermic one, we can see that the hill on the endothermic is much larger in terms of activation energy than the hill on our exothermic. And that makes sense. Endothermic, you got to put heat and energy in. Exothermic, you need to take heat and energy out. And you could imagine that you could see that to get to the other side here, it's not as big of a hill. So we probably expect an exothermic reaction to occur usually a lot of times faster than an endothermic reaction because you do have to put some energy in there to kind of help it along the way. So these are two what are referred to again as energy diagrams. And really that's when you look at an energy diagram, how you can really quickly determine whether or not you're looking at something that is overall exothermic or endothermic process. Exothermic process, like we see here on the screen, reactants always higher in energy than products. Endothermic is the opposite, like we saw on the previous slide. The reactants are lower in energy than the products. And again, that's how you could definitely determine exothermic or endothermic. And again, exothermic gives off heat and energy. Endothermic absorbs heat and energy. Any questions on those energy diagrams? So again, here's those definitions. Endothermic heat and energy is absorbed. And as I mentioned a couple of times here, in terms of values, that is always going to be positive in terms of energy numbers that you calculate. While exothermic heat and energy flows out of the system or is released. And again, heat and energy released. And in terms of value, always going to be a negative value. And that also is something that sometimes people overthink about. And the idea here is that you're given an energy value and it's either positive or negative. You can just simply look at it and know, oh, it's positive, it's an endothermic process, or it's negative, it's an exothermic process. And there's a common sort of unit of energy that we oftentimes will see, and we'll talk a little bit about towards the end of this chapter, but something known as delta H. And delta H is what is known as the enthalpy. And it oftentimes is a representation of a heat of a particular reaction. And again, if you have an endothermic process, your delta H value typically will be a positive value. And if you have a negative delta H value, it will be a exothermic process. Another value that we will see in this chapter that sort of represents heat is Q. Q is also sort of a value that represents heat. And it's the same thing with our Q value. If you calculate Q, which we'll talk about how to do that later in this chapter, and you end up with a positive number for Q, it's an endothermic process. And if you end up with a negative number for Q, it is a exothermic process. So it's really important, and we'll talk about when we talk about the calculations, to make sure that you do certain parts of it correctly, because really the number is not going to be the thing that's going to be affected, but it's actually going to be the sign that's going to be affected. If you just sort of do something not correct, you'll get the same number, but you might not get the correct negative value or positive value, depending on how you choose to do the calculation. And like I said, we'll talk more about that when we get there in this chapter. And again, the last thing in the box on the bottom is the idea of the law of conservation of energy. Again, the energy gained by the surroundings must be equal to the energy lost by the system. So that's that conservation of energy. So whatever is lost should be gained. Again, numerically, when you calculate these things and start calculating them in this chapter, we'll end up the actual same value. The only difference will be the sign. One will be negative, one will be perhaps positive. And very much like we talked a little bit about in terms of phase changes, going from solid to liquid to gas, and going the opposite way, it requires a certain amount of energy associated with it. So as we talked about going from solid to liquid to gas, the solid, for example, is a simple one like the ice cube example. It needs to pick up all that heat and energy from the surroundings. As it does, it starts to melt into liquid water. Again, if you take that liquid water and put it on the stove and heat it up, it will also continue to evaporate, which will make it into a gas. So going from solid to liquid to gas is all endothermic. And in terms of energy values, we're talking positive values as we go that way. Again, for things like delta H, as we'll talk about, and Q. And going the opposite way, gas molecules, again, flying around. They need to lose energy. They're going to slow down and kind of clump together into the liquid phase. And if we continue to take energy out of it, they will not have enough energy to move past each other, as we talked about, and end up in the solid phase. And that is all exothermic as you go from solid to liquid to gas. Again, negative in terms of values like delta H and Q, which we'll talk about in this chapter. Any questions on that there? All right, so take a second and think about, is freezing of water endothermic or exothermic process? So obviously, when we go in the freezing of water, we are going from liquid to solid. And obviously in the liquid phase, everybody's moving around. They're relatively close to each other, but they have enough energy to pass each other, which is why it's liquid. So this would actually be a exothermic process. Again, when it loses that energy or gives off the energy, these water molecules no longer have enough energy really to pass each other. And basically, we now get them kind of clumping together into our solid state. So this, again, would be an exothermic process. Heat and energy is lost. Guys not have enough energy really to pass each other anymore. They sort of come into that solid phase. So take a second and think about this one. Heat is blank, while temperature is... So probably on this one, let's see here. Heat is the flow of energy due to a difference in temperature. Well, temperature is a measure of the random thermal motion of particles. So remember that temperature is really that manifestation of the particles moving around and sort of the measure of that. While again, heat energy is that flow of energy due to a temperature difference, not high grade, low grade. Hot air, it's called the percentage of not just potential energy, is actually a measure more of thermal energy. So I think the best answer here would be B in this particular case. All right, so take a second here and think about each of these and decide whether or not these guys are exothermic or endothermic. Okay, so let's take a look at this. So we want to know are either of these processes exothermic or endothermic, really for the system that's being underlined. So in the first case here, the system is your hand, and your hand gets cold when you touch a piece of ice, and that is because it is going to actually be exothermic here. So when you take your hand and you touch the ice, right? Your hand is warmer than the ice, which means energy is going to be lost from your hand to the ice. And your hand will start to feel cold because of that, because you now lost all that energy. That's why you have the sensation of feeling cold, because it's exothermic in terms of your hand, which is the system. Now, the ice, on the other hand, which is here, so if we move the system now over here to our ice is getting warmer when we touch it. And that's because the ice is actually absorbing all that heat and energy from your hand. And when it absorbs all that heat and energy, in terms of the ice, that's going to now be endothermic, right? Because of that. Water boils in a kettle being heated on a stove. So obviously if we have water and we're heating it, the water is going to gain all that heat and energy from the flame, which means in terms of the water, it is endothermic. Right? It's going to absorb all that heat and energy. And lastly, water vapor condenses on a cold pipe. So condensation is when we go from gas to liquid. And in order for that water vapor to go from gas to liquid, it needs to give off energy, because it will need to slow down to go into the liquid phase. When it does so, because it's giving off energy, that then would be exothermic in terms of the water vapor. And that's sort of like how those are hot pads or hot cold type compressors work, right? Some of them you may break and it does a chemical reaction that's exothermic, which means your hand will gain all that heat and energy and you'll feel warm. Some will do one which is the opposite, sort of a endothermic type reaction, where it has to gain all the heat and energy from you. And again, you feel cold in that sense. Any questions on any of those there? Okay. I got one more. Ice cream melts. So in terms of the ice cream, that also would gain energy, right? We just take ice cream out in the air. It's going to pick up all that heat and energy from the air and the surroundings, and it's going to start to melt, which means it would be endothermic for the ice cream as well. All right. How many of the following are endothermic processes? So take a second and think. So here again, we'll take a look at these. If we activated a warm pack, right, for it to be warm for you, it needs to give off energy to your hand, for example. And because it needs to give off energy to your hand for your hand to gain all that energy and start to feel warm, that means that the actual reaction itself would be an exothermic process to do that, right? So the actual reaction that's happening to do that would be exothermic, as it gives off all that heat and energy to your hand. It would be endothermic for your hand, exothermic for the actual reaction that's happening. Boiling water on a hot stove, as we just talked about, that's going to be endothermic. The water is going to gain all that energy, so that would be one. Melting of ice cube, as we just talked about as well, would also be, so it looks like perhaps two of these would be endothermic processes. Again, the first one is technically in terms of the warm pack, exothermic for the reaction. Again, if you put it on your body or hand or whatever it may be, it would be endothermic for your hand or body in that sense. Any questions on those there? Okay. So hydrogen gas and oxygen gas react violently to form water, which is lower in energy. A mixture of hydrogen and oxygen which is lower in energy, I'm sorry, which is lower in energy, a mixture of hydrogen and oxygen gas or water? Explain. So in this case, as we talked about, just in terms of energy in general, again, the higher something is in energy, the less stable it is, and sort of lower in energy always is sort of a more stable form. And when reactions takes place, one of the sort of the driving forces or one of the reasons why reactions take place is sort of want to bring everything into a state of sort of lower energy. Doesn't mean it's necessarily lower than where everything started. May not always be obviously in that case, but it does try to get to a better state of energy in terms of a lower state of energy. So the formation of water would result in a lower overall sort of potential energy for water than where it started in the sort of separate forms of hydrogen gas and oxygen gas. And really that's why, you know, sometimes reactions do take place is energy wise, it allows things to kind of come together in a more stable fashion than if they were sort of by themselves, especially if they are near something that is very reactive with each other. Again, all that reacting is going to sort of increase the energy, and eventually they will come back down when they come together to form the product to a lower state of energy. So again, the idea behind reactions and those things happening in terms of the energy aspect of it is we always want to create a situation where everybody gets to that lower state of energy than where they started, um, in terms of being separate from each other. It doesn't necessarily mean overall that there's not going to be an overall true decrease in energy or an overall increase in energy of the reaction itself, but taking everybody together, all the elements and the bonds and rearranging the bonds, they always try to manage into the best lower state of energy they can when they come together. And again, that doesn't necessarily mean that it might not always might be more energy than it started with or less energy, but they do try to bond and move around. Even the bonds themselves try to move around to a state where they really maximize the lowest energy configuration they could achieve when they make bonds and we make new things. So like when water is being made, it does so to try to maximize the space between everybody and distance to get everybody into the lowest state of energy that it will be acceptable to kind of stay in. And when we talk about the law of conservation of energy and energy itself, it is sometimes an area of study which is known as thermodynamics. And in Chem 1B, you'll talk more about thermodynamic type properties. But a lot of what thermodynamics really deals with, and again, we don't go into great detail in this class about it, but a lot of what thermodynamics really deals with is the idea of whether or not a reaction will take place. So is a reaction spontaneous or not? And sometimes also people think about, oh, a reaction is spontaneous. That means it must occur super fast. And that's really not what spontaneity means or a spontaneous reaction means. If something is spontaneous, basically what it means is under those conditions, you sort of have the right conditions for that reaction to take place. Has nothing to do with, does it take place really fast? Does it take place really slow? Is it kind of medium in terms of how fast it takes place? So when we talk about how fast or slow a reaction takes place, we really deal with what is known as kinetics, which is another thing you'll talk about in 1B. But when we talk about thermodynamics, it has more to do with under these conditions, would we sort of expect this reaction to take place? And the law of conservation of energy is sometimes referred to as really the first law of thermodynamics. And then, like I said, in 1B, you get really into the second law and third law of thermodynamics. But basically the idea here, the energy of the universe is constant. And that's that idea, as we've been talking about, that if somebody does lose a certain amount of energy, somebody else needs to gain the same amount of energy. Again, we don't really create nor destroy energy. There's this constant moving of energy from one place to the next. And overall, we do remain constant. All right, I think that's probably a good spot to stop here for lecture. So a reminder today, we are going to do, it's lab 4, I believe. And that is mixture, what we've been talking about as well. So that should be good. So if you didn't type here in the chat, please do so. And I'll see everybody in about 15 minutes through the lab lecture link.